I'm very happy to present you today's speaker, Dr. Nicholas Rode from CERN, who's originally from Melbourne, did his undergrad studies, in fact, in Melbourne, before moving to the United States, where he got his PhD under the supervision of Professor Tracy Slater at the MIT. He then got a postdoc position at Berkeley, still in the US, before moving to his current position at CERN. And I guess I'm correct if I say that his research interests are covered a broad range in physics, but the main most important ones can be considered to be dark matter physics, axion physics, and effective field theories, in specifically positivity, unitarity approaches to effective field theory that basically are the arguments that he's going to talk about today in his talk, Positivity and the Topography of the Standard Model Effective Field Theory. So let me leave the stage to Dr. Rode, and that's it.
Thank you, Carlo. And also thank you to Hyun-Min for the opportunity to present here. It's very nice to, I wish I was there in person, but it is really nice to be joining and to seeing so many familiar smiling faces. So what I want to use my time for today is to tell you about some work that I've been doing in the last couple of years with my wonderful collaborator, Grant Remen, which is broadly trying to take these formal ideas of positivity, which I will review for you today, and explaining to you how you can apply these ideas to what I think is in many senses, the most phenomenologically relevant effective field theory of our times, which is the SMEFT, the Standard Model Effective Field Theory. In particular, what I'm going to show with these ideas is that there's actually more to effective field theory than you might have thought if you just embodied a Wilsonian approach. And actually, these ideas can embed, maybe slightly romanticizing, but a structure or a topography onto the SMEFT parameter space, which can potentially be useful when we start thinking about probing this with the LHC, which is a really large activity in the community at the moment. So that's the broad overview, but let me spend the first few minutes just telling you the specific motivations. And also, to be clear, please feel free at any moment to interrupt me with questions if you have them. There's no need to wait till the end. So broadly, I think where we're at it as a field is that, while we might have hoped for many more possibilities, ultimately we have to take the data as it is. And this seems to tell us that at TeV energy scales, the nature as we see it is extremely well described by the basic standard model. Or in other words, the degrees of freedom that I have for you in the middle of the slide there seems to be a very good description of nature at the TeV energy scales. Now, of course, we know that there's more to it than that. I think a lot of significantly about dark matter. And also we know that gravity needs to be embedded into this picture, of course. And in fact, actually, the way that gravity enters the story I'll tell you about today is a very interesting topic. But I can say some words about that if there's interest, but otherwise I'll just be putting that aside. So what I want to focus on today is, we have to take seriously that while we think there's new physics, it really could be the case that we just don't have the energy scales at the instruments we can build to reach the new physics scale. And so because of this, we can think, well, how could new physics show up if we can't actually produce it on shell? Well, of course, Wilson taught us the right way to think about this is that we... no worries. Sorry, if there's any questions, please let me know. I just thought there might have been one there for a second. So what we focus on is this Wilsonian idea of effective field theory, and we apply it to the theory that nature has told us seems to be correct at the TeV scale, which is the standard model. And so then the picture is we write down all the operators that are allowed by the symmetries we have at each mass dimension, where the scaling is then going to be set by this new physics scale, this lambda NP. So, of course, famously at the renormalizable level or at dimension 4, we have the standard model. But then in principle, we can have additional high dimension operators constructed out of the basic field content that we know makes up the standard model. And this could be at dimension 5, 6, 7, etc. So dimension 5, we all know what the operator is there. That's the famous Weinberg operator that is probably most likely the way that we should think about neutrino masses being generated. But then for today, we can think about other operators as well. For example, at dimension 6, one operator you could write down is this 4 fermion electron operator that I'm showing you here in blue. At dimension 8, what types of operators could we have? Well, we could have the same types of electron or 4 fermion operators. We just need to decorate them with 2 additional derivatives to make up the dimensions. And then you can also start to have analogs to like Euler-Heisenberg. So in the Euler-Heisenberg corrections to QED, there's the famous field strength to the 4th terms. And you can have the same sort of operators made up, for example, of hypercharge, which is what I'm showing you in pink there. So in principle, it's an exercise one can sit down and figure out what all the operators are, because you just need to make them out of the basic building blocks we've already discovered, which is in the standard model. So what would a discovery look like in this language? Well, if we measured one of these Wilson coefficients being non-zero, that would tell us that there is new physics there. We just can't reach it on shell, but it leaves a low energy remnant exactly in the way Wilson taught us in the form of these effective field theory operators. So that seems like a picture, and the way that I presented it, maybe it doesn't seem too challenging. But really, the fundamental problem in trying to search for new physics this way is that the dots here that I've put in blue and pink encode an enormous amount of structure. In particular, there's been a lot of debate about this over the years, as I'm sure some of you are familiar with. It was a very challenging issue to resolve, but we now know how many operators there are. And for 3 flavors or 3 generations, there are over 3,000 operators at dimension 6 and over 44,000 operators at dimension 8. So there's an enormous potential parameter space that we could search through to try and find new physics. And while there really could be remnants out there, you might wonder, how can we hope to meaningfully study this space? Especially, essentially from a Wilsonian point of view, it's unstructured. There's just any of these are in principle possible. And if you really want to test the idea of new physics, you need to cover a large fraction of this space.
If that number of the operators are for only the standard model?
This is just with the standard model degrees of freedom, exactly. And one of the things that I should be honest with here, most of the operators actually come from the fermion sector. It's the fact that you have 3 generations that makes this enormous. But even if you collapse that down, you still have a very large number of operators that you need to cover. So if you add additional degrees of freedom, like maybe you'd want to add in a right-handed neutrino if you think that that could be something that is relevant at the energy scales you're studying, or maybe even you want to add in a dark matter particle. That's a very interesting direction people have looked at. That would only add to the number of possible operators you would have, of course. Good, so let me just think about pictorially how this would work. So I'm showing you the parameter space for 2 of these Wilson coefficients, okay? But in the back of your mind, you should be aware that in principle, this is more like a 45,000 dimensional space, but I'm just showing you 2 of this. And what you can think about is that really any part of this parameter space is allowed, as long as the coefficients don't become so large that this expansion I had at the start in terms of mass dimension collapses. So the coefficients can't be arbitrarily large, but other than that, any part of this parameter space in principle is allowed. And what the experimental community has been doing so far is they've been putting some constraints on this space. And in a very cartoon picture, you can just imagine, they might have some 1, 2, 3 sigma contours that look something like this. And of course, so far, we haven't seen any definitive new physics, so the data is consistent with these Wilson coefficients being 0. So then to get some more meat on this, or to really build some intuition, it's always useful to think about specific UV models that could populate this space. As powerful as the SMEFT is, at the end of the day, we're trying to use it to discover UV physics. And so an experimentalist colleague could go and ask their theorist friends, well, can you come up with some models and tell me where they are in this parameter space so I can try and interpret what we're learning from these measurements? And so this is what one could do by looking at various UV completions of this parameter space. Now, to exactly put these on the coupling, specific points on this parameter space, you need to fix all the couplings in your UV theory. So, a given theory would more likely span some region of this space. But for a really specific UV prediction, I can give you some points here. And so, for example, this point right at the bottom right, well, that theory is now seems to be in tension with the data, but some of these are still allowed, as you can see towards the inner parts of the contours. Now, given this information, the conclusion an experimentalist might reach is that theorists aren't particularly creative. What you can see is that you've gone and asked them to try and cover this space, but we have not, the ideas do not really uniformly cover the space of possibilities, even though Wilson told us that in principle, any value of these parameters are allowed. However, what I want to focus on today is that actually there are these surprising constraints that if the UV theory just obeys some basic bedrock principles that we really think it probably should, in particular, it's unitary, it's local, and it obeys the notions of causality, that actually you never could have written down a UV completion that exists outside this blue cone that I'm showing you on the right. And that's the reason why the full space wasn't being spanned, because when we look at the normal types of UV completions we think about, they're actually forced to live in this restricted parameter space. So what would this mean, or what could you even use this information for? Well, for one, you could take this as sort of a theory prior. I mean, I really don't think that the UV violates these assumptions. Of course, we could keep that in the back of our mind. But given this, you could say that in this parameter space the experimentalists are searching in, there is a strong theoretical prior that only certain parts of the parameter space would be populated for new physics. Secondly, and one of the aspects of this that I think is most interesting, is that actually these sorts of results can suggest correlations between different coefficients. So you can see the form of this cone as it's appearing here. You can live anywhere within this, but this tells you, for example, that if you had a measurement of C1, you know something about C2 because the magnitude of C2 is restricted to be less than C1. And in some cases, these coefficients will be measured at very different experiments. So you can now actually, in a very model-independent way, connect different experiments. And then, of course, and I mean, this is getting ahead of ourselves maybe, but I think a very exciting possibility to keep in mind is that if a experimental discovery is made in this space, for example, these contours shrink down to some non-zero value away from the origin, there's the possibility of a double discovery. Again, any non-zero Wilson coefficient is telling you that we need additional degrees of freedom beyond the standard model. So that is the discovery of new physics. But if we find it to be outside this range here, that is telling us that whatever the new physics is, it violates one of our bedrock assumptions that we really think the UV should obey. So it would be sort of a double discovery. We would know that there's new physics and it's bizarre in some fundamental way. Good, so that's the overall motivation here, but that's a completely cartoon description of what's going on. What I want to do in the rest of the talk is make this much more explicit. Importantly, I'll review this idea, although I appreciate that there are experts in the audience, of how you can take these basic bedrock principles in the UV and turn that into constraints on the allowed forms that the IR physics can take. Secondly, though, I'll make it clear to you that there's a lot of nuance in this story, and if you really want to push this as far as you can, there are certain limitations that come up, and I'll tell you about how I've been thinking about getting around these limitations. In particular, I'll divide the talk into 4 sections. The first of these is I'll try and give a somewhat pedagogical review of exactly how you can take these basic UV principles and turn them into constraints on the IR. Then I'll start taking these ideas and applying them to the SMEFT. I'll start out with bosons, and I'll explain to you how there was a connection that we uncovered between these sorts of results and CP violation. I'll then expand that to fermions and tell you about some ideas related to flavor violation. However, all of the first part of the talk will be dominated or focused exclusively on dimension 8 operators. And this is not where we expect the first deviations from the standard model to observe. We would expect it to be at lower dimensions, such as dimension 6. And I'll explain to you why it's challenging to make statements at dimension 6, but still tell you about what we can say at the moment. So with that, let me turn to this basic outline, which is really just trying to explain to you how you should even think about that there's more to effective field theory than Wilson taught us. So in order to do this, this idea can be applied very broadly, but I really just want to stick to the simplest possible example because the physics is still on display there, and then the argument doesn't get complicated by the additional features that you have when you're looking at the full standard model effective field theory. So in particular, let me look at the minimal theory where I know these arguments hold, and that is a single massless scalar field. And I'll imagine that it's invariant under a shift symmetry and also a Z2 reflection symmetry. And by imposing all of this, I know that this theory, beyond the kinetic term, the leading order interaction I can write for it is a dimension 8 operator, which is this d phi to the 4 I'm showing you here. And then there's some unknown Wilson coefficient, which of course has to have inverse mass dimension to the 4th power to make the dimensions here all make sense. So the Wilsonian picture of this theory is that C is encoding some short distance physics. We can't yet resolve what is generating C. There's some UV description of this. But in principle, at larger distances, what we can see is that these phi particles can interact through this, and all of the UV physics that we're not able to access gets parameterized in this single Wilson coefficient here. But although there's this intuitive explanation for this C, in principle, in the Wilsonian picture, C can take on any sign. And really the only restriction that we have on it is that it can't be arbitrarily large, because if it starts to become extremely large, then the perturbative series that tells us that we only need to worry about d phi to the fourth and not necessarily d phi to the 8, for example, breaks down. And so this is the usual notion of perturbative unitarity, that we don't want these coefficients to be too large, but otherwise anything would go. But of course, as I laid out at the outset, there can be more to this picture. And what I want to run through you now is just that if you push these arguments through, you'll find out that C has to actually be positive, that negative values cannot be generated by a naively consistent UV theory. So there's two ways that have been presented in the literature for generating these types of arguments. The first of these is what I would call sort of an argument that proceeds through dispersion relations. Essentially, how this argument goes, just to give you the gist of it, is that the presence of this coefficient C allows you to write down a scattering amplitude for the phi quanta. So you can have 2 phi to 2 phi scattering. And then from this scattering amplitude, you can invoke unitarity to connect this amplitude to a cross-section. And then because we know cross-sections are positive, you'll ultimately be able to conclude that the coefficient C has to be positive. So this is actually quite an old argument. It dates back to the chiral perturbation literature and some pioneering work by Pham and Trong in the mid-1980s. So there's another way of thinking about these, and that is that actually this Wilsonian picture that C emerges from short distance physics is really not the right way of thinking about it, because it's not really a Lorentzian way of visualizing this. In particular, you can think that, phi in the absence of this interaction sits right on the light cone. And the presence of this C can push you one way or the other off the light cone. And if it pushes you the wrong way, this phi can now propagate superluminally. And in particular, you can then start to cook up causal, you can generate these causal paradoxes that we think shouldn't be allowed. And so you can exclude these values of C. So this causal propagation argument really feels fundamentally different to the dispersive one I showed you on the left. And this one appeared most famously, I think the first time I'm aware of it being discussed was in a paper by Adams and collaborators in 2006. And exactly why these two arguments often give the same result, I think is still an open question. It's very interesting. So I'm happy to say a few words about the causal propagation argument if there's interest, but really because I think that the dispersive approach is on the firmest footing. It is the easiest one to extend, as I'll focus on today. I'll run you through how that argument works in most detail. So as mentioned, the starting point here is that we can write down a 2 to 2 scattering amplitude. And so to do this, I need to actually sit down and do some calculations. So let me work explicitly calculating the amplitude we get for this in the presence of this high dimension operator here. Also, this gives me a chance to write down my conventions. I'll mostly stick to these throughout the talk, but occasionally I actually flip around. So please feel free to ask if it's not clear what's going on. So I'm working in a convention where all the momenta is taken as incoming. And then also you can see from this choice here, I'm working in the mostly plus metric. Grant won that argument coming from a formal background. And then you can see that this is how you define the normal Mandelstam invariance. And I'm taking all of these fields to be massless. So S plus T plus U vanishes. So another point that will actually play a role throughout the talk is invoking the notion of crossing symmetry. Now, of course, there's various ways you can use crossing symmetry, but when I talk about this in the talk, I'm always going to mean crossing the 1 and the 3 states, which is the top I'm showing you here. And in particular, if you stare at the momenta, you'll see that if I cross 1 and 3, it's equivalent to swapping S and U. It leaves T invariant. Good, so now I need to write down an amplitude. And the only complication here is you need to keep track of the symmetry factors because all of these phi's are identical, but it's not that difficult to do so. And when one does, you find that you can write down an amplitude, which of course is only a function of Mandelstam S and T, because U is not an independent parameter because it's related to the others as I show in the blue box. And you get this result I'm showing you here. Additionally, it will be useful for reasons that you'll see shortly to evaluate this amplitude in the forward limit where the two particles are exactly coming to, initial particles are coming in the same direction. In this case, when you evaluate the forward limit and the scattering proceeds where they just pass straight through each other, you'll find that you send T to 0 and U goes to minus S. So in this case, the U just gives the same contribution as the S, and you end up with an amplitude that has this form here. Also, one can check in the forward limit. Essentially, what you're doing is you're swapping, U just becomes minus S. So in this case, crossing symmetry is just S goes to minus S. In particular, in this amplitude here, it turns out it's invariant under this crossing symmetry in this particular example. Good, so we've got this amplitude. What can we do with it? Well, the thing that it turns out is useful when thinking about these dispersion relations is take this forward amplitude, which is just a function of S, and analytically continue it to complex values of S. So that's what I'm showing you in the plane here. I'm looking at this amplitude, but analytically continue to complex values of S. So I've got the real axis here and the imaginary axis on the vertical. So what is important is if the UV theory is analytic, so just to step back and specify, when I'm thinking about this amplitude here, I'm now talking about this amplitude in the full UV theory, which I may not know how to evaluate. The calculation I went through on the last few slides is just how to compute that amplitude in the specific EFT. So that should really only hold at low values of Mandelstam S, for example. But if the full UV theory is analytic, or equivalently if it's causal, then what you find is that the amplitude will only have discontinuities along the real axis here that I'm showing you. In particular, the forward amplitude will have discontinuities on the positive real axis associated with single particle exchanges and multi-particle exchanges in the S channel. And then it will also have a branch cut on the negative axis associated with these same processes occurring in the U channel. Now, if you think about this for a moment, you might be surprised by this, because if you think about the possibility of unstable particles, you know that they can have poles off the real axis. But actually, you can check. I mean, as soon as you have branch cuts, this function is has multiple branches, and you can check that actually where those poles occur is not on the primary branch. And these sorts of subtleties were actually, I mean, part of the pioneering work that was done on this notion of the analyticity of the S matrix back in the 50s and 60s in some of these papers I'm showing you here. Also, as much as I'm trying to go through this carefully, let me admit that there's many subtleties that I'm going to be brushing aside, but often I'll try and keep track of them in these blue boxes at the bottom of the slide. So please have a look there or ask me if you have any questions. So as I mentioned, what I'm studying here is the amplitude in the full UV theory, which I don't know, and so I can't compute. But one thing I can say is that if I go down to very small values of this S parametrically, if I get small enough, eventually the EFT should be a good description. And so there I should know how to evaluate things, because I can use the amplitude I had from previous slides. In particular, I'm looking at Mandelstam S values where I are well below the new physics scale. So then if I want to study what this interaction, or in particular isolate this Wilson coefficient C, what I can do is I can look at the amplitude and divide it by S to the third power. By doing this, because recall that the amplitude went as S squared in the forward limit, I'll isolate the coefficient I care about as a simple pole. And so just by using basic properties of contour integration, this amplitude here will be linked to this force C. So that's going to start my argument off by looking at this contour here. But if you've ever done contour integration, you know what the next step is. I'm going to blow this contour up to as large as I can. And because I know where these discontinuities are, the claim is that while I know what the value is in this small contour, because I can evaluate it in the EFT, the answer must be the same when evaluated over the large contour. However, now for most of this contour, technically the amplitude that enters into the integral here is the UV one, which I don't know. So let's write this out. I can break this into some boundary contributions and also an integral on either side of the discontinuities on the positive and negative axis. The amplitude at infinity I can throw out because just basic principles tell me that the amplitude dies off fast enough that these contributions won't contribute. And then all that I have left is the integral over the discontinuities on the positive and negative axes, as I'm showing you here. Now, it turns out that if I invoke this crossing symmetry, I can rewrite the amplitude over the negative part in terms of an integral over positive S values. This is the exercise I've gone through here. And because for this specifically simple theory, this crossing symmetry actually left the amplitude invariant, I can combine these two terms together exactly. And this is how I essentially kill off this factor of 2 here in this argument. Next, if you go back and stare at the definition of the discontinuity, which is the difference above and below the amplitude here, you can realize that this is related to the imaginary part of the amplitude, which is what I'm showing you here, up to a factor of 2i. And so that's how I've gotten rid of the factor of I and where the factor of 2 came from. But now if I assume that the UV theory is unitary, I know nothing else about it in principle, but if I assume it's unitary, I can invoke the optical theorem, and then I get this relation that I'm showing you at the bottom here. And now note, there's been a number of steps in this manipulation, but what we can see is that this final result we have has to be positive, whatever it is. This cross-section is a positive quantity by definition. The full integrand is positive, and I'm integrating it over a positive region. And so because of this, if I now do a connection between where we started and where we've ended up, unless one of the assumptions that was invoked in this line of reasoning is violated, this coefficient must be positive. And so this is how these dispersive types of arguments proceed. So before I move on to talk about specific applications, let me pause and tell you what were really the essential ingredients in the argument. To begin with, I needed a 2-to-2 scattering amplitude. Otherwise, I can't invoke all these basic properties like analyticity that were heroically proven in the 50s and 60s. So that means that the new operator I write down has to support some 2-to-2 scattering amplitude. And that means that you need 4 fields effectively. So you're going to need operators that have 4 combinations or 4 appearances of the various fields in the standard model. Secondly, it was actually critical at several steps that the amplitude scaled as s squared, or equivalently had 4 powers of momenta in there. I didn't make a big point on this, but recall I told you that I could throw away this boundary term at infinity. Actually, if, for example, we only had 2 powers of momenta or an s scaling, I would have had to divide the amplitude by s squared, not s cubed. And then actually these basic arguments like the Froissart bound or causality would not be enough to throw away this contour at infinity. And I would have had to keep track of it, and it would have made my life more challenging. Further, recall that when I invoked crossing symmetry, I was able to combine the U channel and the S channel together. However, if I had 1 less power of S in the amplitude, instead of S cubed here, I'd have S squared. And actually, these 2 terms wouldn't come together. They'd come in with a relative minus sign. And in this specific case, they'd exactly cancel out. But more generally, you'd have a minus sign between the 2 terms that makes it very difficult to claim that something's positive. So I'll come back to discuss how we can tackle some of these challenges later in the talk. However, you can already see that we're going to get this argument to go through as expected, we're going to need either 4 derivatives, or if you remember that fermions secretly have a square root of momenta in them, so we can also make this up with fermion bilinears here. But this tells us that we're going to need something like a dimension 8 operator, such as b to the 4th, or this 4 fermion electron operator with 2 derivatives if we want to apply these arguments. So this already gives you some sense for why dimension 8 is really the easiest place to apply these arguments. So that's really the heart of the physics that's going on here. What the rest of the talk is going to be is taking this and applying it to beyond to a more complicated example than the scalar theory, like the examples we have in the standard model. But please let me pause for a moment just to check if there's any questions on how really the heart of the physics is operating here.
I have a naive question, very naive, but when you require that this C coefficient, your Wilson coefficient theory is positive, are you requiring that it is positive? For example, if I adopt, as you say, a Wilsonian view, so I'm adopting a Wilsonian view where it emerges from high energy physics. So there is a running that encodes the way it evolves as more and more fluctuations are included. Are you assuming that this positive in its whole running, or maybe there can be a crossing of the zero? Are you just implying that it is positive at low energies, or it must be positive in the whole range of its running?
No, this is actually an exceptionally good question, and it's one of the subtleties I'm just brushing under the rug here. So what I'm ultimately requiring is that it needs to be positive in its entire running for this thing to be sensible. So I'm talking throughout this talk, I'm just treating these Wilson coefficients like a number, but of course they're not exactly as you say, they run. So in the talk here, what you can really think I'm doing is I'm essentially just looking at these C's at the matching scale, for example, so that I can just put these running issues aside, but they are definitely there. And in principle, what you need to check is that as you run these things, the positivity is maintained. In fact, I have a backup slide in this that I can show later, but there's been some work done checking that, for example, the dimension 6 SMEFT causes the dimension 8 SMEFT to run. And you can ask, does the running that it induces maintain this positivity as you scan through? And you can check it, and it does. I mean, this is exactly something you have to check. In fact, broadly, the intuition is that if you run from the UV to the IR, you just get safer. You can show that you're just adding a positive contribution. So, for example, if you have a bound that is satisfied in the UV, then as you run to the IR, generally things will just get safer and safer and safer. Like if you had a slightly positive quantity, you'll get more and more positive. But if you're in the IR, it's not always obvious, because if you reverse that argument, as you run to the UV, things can get more, like, can move away from this. And you can worry that in certain cases, you can run this theory into a forbidden part of the parameter space, which shows that something's been going wrong. So actually, there's a huge amount of work on this specific question that you're raising, but I wasn't planning on tackling it directly today. So I can point you to some references afterwards if there's more interest, but it's a very, very interesting topic I'm just not diving into.
Thank you.
No, thank you for the question.
That means that this positivity bound depends on this IR circle that you are drawing, right? So you can make a small or larger, depending
exactly. Yeah. So it really, in truth, it depends where have you put this circle. And also, you know, in a real UV theory, you could put the circle also like on where it has the branch cuts here as well, because you could have states in your theory, you know, in the EFT you're studying that can be exchanged. So it's not always the case that you need to get rid of these things. But through these arguments, you can really show that as you move the circle smaller and smaller, all of these results get safer. It's as you push to the UV that danger could occur. And this is exactly sort of what you might expect anyway. But yeah, it's exactly as you said.
Also, are there any finite contributions to this argument? Like there's some poles, I don't know, different positions, some weird form of the Mandelstam variable, I don't know.
Poles can definitely give finite contributions, and they can be a bit fiddly to incorporate into this argument here. So as I said, really the way I'm presenting it here is just the simplest way of thinking about this, but people have gone through this in much, much more care and shown that you can account for all of these finite contributions, and I'm not lying to you too much in the way that I'm presenting it here. Yeah. But no, all these subtleties need to be addressed, and they have been, but the argument still roughly holds as I'm showing you here. Yeah.
Okay.
Good. So yeah, hopefully you have some sense for the basic physics, but I think as the questions are really hitting, there's more going on here. But nonetheless, let me take this basic argument and now try and port this to the standard model effective field theory. So as I've already told, sorry, go ahead. Is there a question?
I don't know if there was a question I'm asking.
Yeah. So can you hear me now? Okay, sorry.
Yes. Sorry. Yeah. Hi, Sang-Hoon.
Yeah, I'm sorry. Yeah. So naively, so here, lambda new physics can be regarded as the lightest particle of the new physics, right? And so what if there is some new physics particle whose mass is lighter than some standard model particles? So do you?
That's a very interesting question. I mean, the immediate thing is you've made a mistake, right? When you write down an effective field theory, you need to include all the infrared degrees of freedom, and you've missed it. Right. So I think it's an interesting question to study, and it's not one that I've seen looked at carefully. What sort of results would you induce if there is IR physics that you've missed? Like, for example, you might think there's an axion in the theory or something like this, and maybe if that can induce, like, what that will manifest itself as intuitively is non-locality, because this thing can mediate long-range interactions, for example, that is just not, you contact operators just cannot reproduce that physics. But exactly what that does to this, it's not clear. But I mean, in short, you've made a mistake. You've written down the wrong EFT that you're studying is what you've done. But exactly what that induces, I'm not sure. It'll violate locality is my suspicion in the way that I described. But how exactly that shows up, I think, is an interesting question I've wanted to look into. Yeah.
Okay, so can I say, I mean, you showed the diagram of a C1 and C2, and if there is some experimental leisure which is outside of the positivity bound, even if it does not violate any principles of UV, it could be just the fact that we do use the wrong IR
I think that that's possible. And in fact, if we saw this, that's probably my first suspicion, but it has violated one of the tenets, right? It's violated locality, but in a very, in a not particularly deep way that we forgot a long range degree of freedom in the description. But no, I think it's a really interesting question to think about. Yeah.
Okay, thank you.
Excellent. Thank you for all the questions. So let me now turn to applying this to the SMEFT. And in particular, as I said, I'll start out with bosons. So let me not spend much time on this, but let me be upfront that where Grant and I spent most of the effort in this first paper was getting a complete basis of operators that we needed to deal with. I mean, sort of as mentioned in the case for when I was just answering Sungwook's question there, you need the correct basis to work with, or you have errors from step one. And as I told you, we really think that at dimension 8, these arguments are most straightforward. So the work that Grant and I needed to do was enumerate this basis because it hadn't been done when we first did our work on this. So let me not dive into it, but this is the basis that we ended up with. And there's all sorts of surprising relations that you know, I'm sure many of you have heard of these equations of motion you can apply that relate many of these. So I definitely do not have time, but even if I did, I wouldn't do this to you. I mean, what one can do is go operator by operator and start applying these bounds here. But I think that may not be the most interesting talk. So instead, let me just focus in on a very minimal aspect of this basis, just the hypercharge operators at dimension 8, the b to the 4th I'm showing you here, and study what we can say for them. Because even there, we'll find something that I found very interesting and actually will give you a flavor of what the results look like to the entire space I'm showing you here. So I could talk about this in terms of hypercharge, but if we're talking about a U1 theory, I think it's a bit more fun to think about this in the context of QED, because really the argument goes through in exactly the same way. So in particular, just as we had for the scalar, I've got the kinetic term for QED, but at dimension 8, because there's a bit more structure here, I can write down in principle 3 operators. 2 CP conserving operators, that's C1 and C2. These are the famous Euler-Heisenberg operators. And then in principle, there could be a CP violating operator, which is this F cubed F tilde that I'm showing you here. So how can I go about studying these? Well, I really can apply the exact same argument that we had for the scalars. But now I have an additional degree of freedom that I can talk about when doing this scattering experiment, which is the polarization of the photons I'm sending in. In particular, if I send in the 2 photons with parallel polarizations, you can check because of the presence of the Levi-Civita that enters into F tilde, I'll kill off any FF tilde term. So I'll just be left with C1, and shock horror, you find out that C1 has to be positive. Similarly, if I scatter perpendicular polarizations, I'll kill off any F squared term, which kills off C1 and C tilde, and I'll find C2 has to be positive. So that's interesting, and actually that was a result that was known. However, I think one thing that Grant and I wanted to study is we wanted as many bounds as we could. And so you can ask, is there any way of getting C tilde? Now, there's no obvious choice I can choose that will turn off C1 and C2 and just leave C tilde. So it's not obvious I should get some positivity result here. However, if I look at any scattering angle of the angle between the polarizations that's not parallel or perpendicular, I'll have all 3 operators at once. So I might expect some result that depends on all of them. And also just to say, these ideas aren't completely ridiculous. I mean, in the case of Euler-Heisenberg, there's a very famous value of C1 and C2. And this is what you get when you integrate the electron out. And you can check explicitly that both of these numbers are positive. So what I want to focus on now is what we can say about C tilde. So as I said, the right way of thinking about this is just to scatter at some arbitrary angle between the polarizations. Excuse me. I can write down what this amplitude is. It scales as S squared as claimed. And then the point is that whatever is in this brackets here by the earlier argument is what has to be positive. And it has to be positive for any value of theta. So again, if I choose theta to be 0 or pi over 2, I recover the results we had earlier. But if I scan over all the allowed values of theta, I find that if you choose this specific angle here, you get the strongest constraint on C tilde, which takes the form I'm showing you here. And so indeed, it involves all of the Wilson coefficients as I claimed. So I think this type of result is very interesting. It's the exact sort of one I mentioned to you earlier on, where you can really correlate different types of experiments, because usually CP violating effects are measured at different instruments to CP conserving. And indeed, it has this type of cone type structure we described earlier on. It says that you need to live within this cone. So any measurement of C1 or C2 tells you something about the allowed values of C tilde that can be taken. Or if you instead fix all of the Wilson coefficients to just be 1 divided by the relevant scale, it tells you that the scale of the CP violation must be larger than the scale of the CP conservation on very, very general grounds. Now you can ask, what could you do with these types of results? Well, in some very interesting work by Marco Guerrero, Perez, Savaroy, and Sarek from 2021, they looked at, well, there's a number of proposals to actually measure the Euler-Heisenberg terms. Some of you may be aware, but for those of you who aren't, I found it quite shocking that despite that being a very, very old prediction, we've never measured light-by-light scattering below the electron mass, although there's many ideas about how we might do this. And for one of these ideas, it's also been discussed that you could actually measure the CP violating interaction that I mentioned. But already, because we have some constraints on the size of the CP conserving interactions, we know that the CP violating one can't be too large. And so this tells you that wherever these CP violating effects might emerge, they have to be below this, for example. So it already tells you something about the experimental parameter space. And the C1 and C2 measurements do not come from the types of experiments that would probe this. So it's really correlating different instruments, as I mentioned. Now, we can apply this same type of argument to the entire SMEFT parameter space that I mentioned earlier on. You get a large number of bounds, but they all come in the flavor that I've told you. Some CP even coefficient is positive, or some product of CP even coefficients has to be greater than a CP odd coefficient. So really, this seems to be the interesting language or the interesting formula of the constraints that was already apparent in just the hypercharged sector. Furthermore, something that we found that is interesting is sometimes these bounds are very straightforward. In principle, we have to allow all of the operators to be there, but you can get some very simple bounds like that certain Higgs operators on their own must be positive. It's not always a combination of many operators that comes in. The other thing that we went through here is check, just as I showed you for the integrating out the electron, that if you integrate essentially any state out at one loop, then all of these bounds are satisfied, which was a very non-trivial check of what we were doing. Just to give you one place where I can imagine invoking these types of results, these dimension 8 operators can modify the interactions between 4 electroweak vector bosons, as I'm showing you here. And through the diagram, I'm showing you the LHC has actually been probing these effects. For example, they set some constraints on 2 of the operators, the Higgs ones I'm showing you here, in the form of the yellow circle at 95% confidence. And what we can do is we can say, well, from a UV perspective, I can exactly put these constraints on this space. For the specific operators they considered, the constraint doesn't have a very interesting shape. It's just one side is allowed and the other side isn't. But in principle, this is exactly what we were talking about being able to do. In fact, as we dove into this, we found that the basis that the experimentalists were using was incomplete. In fact, they were setting bounds on one operator that you could show was exactly 0. But I mean, this is just, again, a reality that these basis issues are really challenging. But this is actually a space where I think the high-Lumi LHC is going to make significant improvements. There's really a target to significantly improve our measurements of these 4 vector boson interactions. There's only some of these have been seen for the first time. And this is something where I think I could imagine this being deployed in the coming years. So that's all I wanted to say about bosons. And I think the main surprise that Grant and I had there was this interesting interplay between CP conservation and violation. But next, let me turn to fermions and tell you about what we discovered. And in particular, there'll be some interesting statement I can make about flavor violation. So again, what we did in the paper was we spent a lot of effort getting the minimal basis and setting bounds on all of these operators. But I think just to give you the core part of the physics, let me focus on what is really the simplest operator here and tell you what we found there. And in the case of 4 fermion operators at dimension 8, to me, the simplest operator you can write down is this one that I've written for you here. It's actually just a single operator by some counting, where we have these 4 right-handed electrons, but we've also had to decorate them with 2 derivatives to get to dimension 8. Now, actually, there's more than one operator here in a theory that has NF flavors, because in principle, any of these, I can index these over the different flavors I have in the theory. It could be electron, muon, or tau type. Or higher if you allow for more general flavors. And so I have to have some general matrix in front of that to encode the different flavors that could enter into this Wilson coefficient. So what I'm going to do now is, in order to access some of the interesting information about flavors, previously we scattered an arbitrary angle between the polarizations. But in order to get access to the flavors, let me scatter an arbitrary superposition of the flavors. So you can imagine what I'm doing here is in some thought experiment, I'm preparing my initial state to be some admixture of, say, like an equal amount of electron or muon type right-hand neutrino, and that's what I'm sending in my scattering state. But in this thought experiment, I can imagine preparing any general admixture, and that's what I'm writing as this alpha and beta. So then if I do the calculation, I find that the scattering amplitude has the form that I'm showing you here. And so again, the S squared coefficient has to be positive, and so I conclude that this object here has to be positive. And for example, if you reduce this down to one flavor, you'll get that the coefficient of this operator had to be positive, which matched a known result by Bellizzini, who first really pushed these ideas to fermions. So what is this bound here? What is the physics of this? Well, this whole result is essentially independent under how we define what we mean by flavors. So I could always do some flavor rotation to make one of the external states that I'm scattering trivial, or equivalently, you could have just imagined simplifying the statement by just taking the one state to be purely electron type, which is equivalent to just making this a delta function. What happens then is this is now a 2-index matrix because I've fixed the other two indices. And the statement is that this 2-index matrix, when contracted between beta and beta star, must always be positive. Now, if you remember your linear algebra, what that actually tells you is that this CNP has to be a positive definite matrix, which is the notation that I'm given here. And so that imposes a bunch of structure on this. In particular, it tells me that the diagonal entries in this matrix have to be positive, and that it also has to have positive determinant. So what does this mean? Well, if we now take these statements about a matrix and convert it back to some physics, we find that the coefficient for electron type scattering, purely electron type, is positive. The coefficient for muon electron is positive. However, if we look at some interaction that violates flavor, which is like this one here, that would mediate E bar goes to mu E bar, then that's the size of that interaction is bounded by the product of the two flavor conserving interactions that I'm showing you here. So just as previously we had CP violation bound CP conservation, here we see flavor violation is bounded by flavor conservation. In fact, actually in these operators, you can also violate CP, and you can show that it's only the interactions that violate flavor that can also violate CP. So actually, as a subset to this statement, we have the exact same results that we had for the bosons to begin with. And I should also say this simplified way of understanding what's going on here is not actually something that Grant and I had back in 2020. It's actually a result of some ongoing work that I'm doing with some people who are either at CERN or have been at CERN recently, Shankar Banerjee and Sophie Renner, and is in some work that we hope to have out later this year. So also, I mean, if you look at this in the most general space, ultimately, the physics statement is just that this matrix in these two indices has to be positive semi-definite technically. But then once you go to some arbitrary flavor space, it turns out that the structure can be quite rich. And let me not dive into this exactly how I've defined this, but really this is just showing if you look across the space of possible coefficients, you can get quite interesting structures in terms of what parameters are allowed and forbidden. And in this case here, you can see that we've sort of lifted this cone structure to an ice cream cone structure. I appreciate I'm not giving you a detailed explanation of what's going on here. In the interest of time, let me just move on, but I'm happy to describe if anyone's interested. So in the last few minutes I have left, let me just say a few words about how we can push these ideas to where we really think the deviations in new physics, the first signs of new physics should emerge, which is at dimension 6. The short statement is, at dimension 8, we can make very generic statements that really only require bedrock assumptions. But at dimension 6, we can say some things, but we'll need to invoke more dramatic assumptions in order to say that. So I'll just be upfront with that, and I'll run through how this works here. So let's look to extend this original dispersive argument to dimension 6. So if I write out the dimension 8 argument in more detail, so in the scalar case we went through earlier, there was no external flavors or quantum numbers we needed to keep track of. But in principle, if we're looking at this fermion scattering or the photon scattering, there were external states we needed to keep track of. So I can label those as alpha and beta for the 1 and 2 state. And because I'm thinking of a forward elastic scattering, I don't need to talk about the final state. They're fixed by the initial state. And then if I write out the dispersive argument, I find I get the amplitude, but also the crossed amplitude here. And if you have quantum numbers for the external states, the crossed and the initial amplitude aren't the same, so you have to keep track of both of them. But independently, these two imaginary parts can be linked to some cross-section, which is positive. So this whole quantity is still positive. So the S squared part of the general amplitude is positive, and that's what I've been implicitly using in the second two parts of the talk today. So I can just write down the equivalent result at dimension 6. The amplitude will now scale as S. So I need to replace this S cubed with an S squared. As I advertised earlier on, though, there's going to be two modifications. I'm going to have a minus sign that comes in between these two terms. So I'm going to have the difference of two cross sections, which isn't generically positive. And also I'm going to have this boundary circle at infinity contribution, which again just isn't generically has any definite sign. It just is what it is. So this is the result I can write down, but I'm not immediately going to be able to say that anything is positive because I've got signs, a difference of two positive quantities, and I've got a contribution that has indefinite sign. So just to give you some intuition for what's going on here, because this is slightly different to what we had above, you can imagine a tree-level UV completion of whatever amplitude gave rise to this dimension 6 operator. For example, you could imagine a tree-level state being exchanged in the S channel, in the U channel, or the T channel. Now, whatever is going on in that theory, there could be arbitrary complications in the numerator here. Ultimately, what these dispersive arguments keep track of is really the location of the poles in the branch cuts. And if I just have a tree-level UV completion, I just have poles. So then you can ask, for these types of UV completions, how are they showing up in the dispersive argument I'm showing you here? And actually, they can be matched uniquely, which I think, at least for me, gives me a lot of intuition for what's going on. If you look at the imaginary part of this term, this can only show up in this contribution I'm showing you here. For the U channel, it comes up from the other side of the contour, so exactly as you would expect. This is where this comes in from this minus sign. But the T channel is really actually the problem here. The T channel is the one that must give rise to a boundary term. The reason for this is, remember, we're studying a forward amplitude. And in the forward limit, you send T to 0. So really what this term is, if you look at the imaginary part, it's a delta function of minus m squared. But there's no kinematic condition here. And as long as m is greater than 0, which is the scale of the new V state, then this delta function has no support. It's just 0. So the imaginary part of this amplitude is 0. And that means if you want to reproduce this term in this dispersive argument, it could never show up in these two terms. It can only be reproduced in a boundary term. So really, this is telling us that these problematic boundary terms are associated with T-channel states that we might exchange. Now, in the interest of time, let me not go into all the details here. Unfortunately, I haven't managed my time as well as I would have liked. Just to say, we could also go through an argument to extract the Mandelstam T coefficient of the amplitude. There's some subtleties you need to keep track of for fermions. They're usually the problem here. But in exactly the same type of dispersive argument can be written down. And I'll make use of this in a moment, but let me not go through all the details now, given time. So what Grant and I tried to understand is, can we combine these two dispersive arguments to say anything? So what we will do is, let me just focus on fermion scattering, and let me assume that the UV is such that the amplitudes die off fast enough that I can throw away these boundary terms. But that just isn't generic. Let me be fully upfront about that. As I told you, if the UV completion is a state exchanged in the T channel at tree level, then you will get boundary terms. So it's not generic, but one can say, well, let's imagine that this did happen. What can we say? Because these boundary terms are very difficult to deal with. Well, what Grant and I showed is that you can combine these relations to actually give you a sum rule at dimension 6, which is what I'm showing you in this orange box here. And this says that the form of the Wilson coefficient, which is what's given on the left-hand side, is given by a difference of two different partial waves. You have the scalar partial wave minus the vector partial wave. And that means that if in the UV, the theory is dominated by a scalar, then you'll get one sign in the IR. Whereas if it's dominated by a vector, you'll get the opposite sign if the boundary terms can be neglected. So this tells you that the sign in dimension 6 certainly doesn't have to be positive, but it can be a relic of the spin of the state in the UV. But what is interesting about this is that these arguments that required us to have flavor violation be smaller than flavor conservation didn't require the Wilson coefficient to be positive. They just required it to have a definite sign. So in either event here, you would exactly have, again, these types of flavor violations being bounded by flavor conservation, even at dimension 6. So that was all quite abstract, I appreciate. So let me just try and make this concrete. So let's imagine if we study the dimension 6 analog of the dimension 8 operator I showed you earlier on. So I just pull the derivatives off. Then this is what the Wilson coefficient I would get. And I would find that this object will take a sign that is controlled by the spin in the UV. So I can study an explicit UV completion just to see what would happen here. I could imagine exchanging a scalar in the U channel here, or technically I could exchange a vector in the S or the T channel. And just as you might have expected, you can check that the scalar in the S channel gives a positive contribution. The vector in the U channel, the scalar, the vector for the way I've set this up will give a negative contribution. And that the T channel vector gives this indefinite sign term. So it's exactly what you would have expected for a boundary term. So then this raises the question that I've been trying to understand recently, and this is what Shankar, Sophie, and I have been digging into. I can make a statement that it seems under some generic conditions, I can have flavor violation still bounded by flavor conservation at dimension 6. But as you must have appreciated, the argument requires more assumptions. And so you can ask, well, then probably you can violate this. And so it's sort of interesting. What would it take to violate this and allow you to have like arbitrarily large flavor violation at dimension 6? But essentially what we've understood is that it's hard. It is possible, but it is hard. For instance, it's not enough just to have a vector in the T channel. You can show that theory still satisfies these types of constraints. Actually, what you need is you need multiple states in the UV tuned off against each other to kill off the flavor conserving part and leave a large flavor violating part. In particular, you need states of different spin, and you need to tune their couplings and mass together to actually violate this constraint. So this tells me that generically you still expect this correlation we saw at dimension 8, but if you did see a violation on that, that's actually telling you that there's some interesting structure in the UV. So that I appreciate was a lightning walk through what's happening at dimension 6. But if you get any takeaway from that, I would just say that there are statements we can make here, but they're less robust. There's still things we can learn about what's happening in the UV, but more assumptions need to be invoked. But also, I think, especially on the dimension 6 front, there's a lot left to be learned about what we can do here. And this is a space I'm very excited about exploring. And to step back further still, hopefully I've left you with some impression that these ideas of positivity, although they've mostly been applied in a formal literature so far, really can say something about phenomenologically relevant EFTs like the SMEFT that I've told you about today. So I apologize for running a little bit over time, but I really thank you for all your attention, and I'd be very happy to take more questions if there are any. Let me leave it there. Thanks.
I have a
Let's thank Dr. Rod, and go Sonchik if you have a question.
I have a question about the page on the bosonic bound that you say that for theta, the best bound is given by arctangent over what format. I wonder if there is something systematic way to get the best bound.
Good. So, I mean, maybe I'm being overly honest here, but how did we determine this bound originally? I'll tell you, I put this expression into Mathematica, and there's a function called reduce, which can determine these sorts of things. And that's exactly how I got the angle initially, just being completely honest with you. But then you can ask ahead of time, how could have I known this? I mean, to say something, it's not shocking that the angle should depend on the other coefficients. Because what you want to do is you want to get the strongest bound on this in the presence of all three of them. So depending on their relative sign, you can imagine that you may want to tune more towards one than the other to get the strongest possible bound. So I don't think that's shocking. But actually, in some other work that I have at the moment, I've realized that you really can. I mean, in particular, the person who realized this was this fantastic fellow here at CERN, Mark Rambau. He showed you really can rewrite these results in the form of some matrix has to be positive semi-definite. And then once you've done that, what does this look like? It looks like a determinant of a matrix, right? It is the sort of form that's coming out here, where that's the diagonal and this is the off-diagonal term. So that was always my suspicion, but I didn't exactly know how to show this. Marcus taught me how you can take the results we had, and you really can rewrite this as the form of a matrix can be positive semi-definite. So this isn't work that's out yet, but I think that ultimately that is how you can do this more systematically. Secretly, all these results come back to some matrix has to be positive semi-definite, and so it has to have a positive determinant. But in the specific, very physically motivated way I constructed it here, you just have to scan to find the scattering angle. And being honest, that's how I found it originally. But yeah, I think there is a deeper way of understanding it, which is probably what you're hoping for. Yeah.
Thank you. I think you know your secret.
Oh, no. No, that's okay.
We have a question from Kimiko.
Yes. Thank you very much for Nick for last year for your kind discussion in the last year at Jeju.
Of course, no worries. Good to see you, Kimiko.
Yeah, thank you. Nice to see you again. May I ask a question? In the boson and both the boson and the fermion dimension 8 operator case, you got the violation Wilson coefficient scale is small, number is smaller than the CP even or flavor conservation case. And you found that the cutoff scale of the CP violation or flavor violation is larger than the CP even or flavor conservation case. Yeah, it was very interesting. What is the reason that the positivity suggests that the violation scale is larger than the conservation scale case? Maybe you mentioned already.
No, I think it's a really interesting question. Like, why is this occurring? So it depends. Like, you can have different levels of expectation here, right? Like, if you try and write down UV theories, you generically find that this just occurs. I mean, in most UV theories, like CP violation, I'm being very vague here. It doesn't always work this way, but sometimes it's associated with some phase in the UV, and the real part of this can be associated with some conserving part, but the imaginary part is sometimes linked to the CP violation. So in those sorts of theories, it's not that shocking that something like this comes out. And when I was talking to some phenomenology colleagues about this, they're like, yeah, but this is exactly what I expected. So it's maybe not that shocking. But proving this in general is not only hard, it's impossible. As I mentioned at the end, you can write down counterexamples to these statements. At dimension 6, I can come up with UV theories where you can violate this and get arbitrarily large CP violation without inducing some CP conserving effect. So the fact that it comes out in this way at dimension 8 is, therefore, I felt a little bit surprising. Yeah. Why is this happening? I still don't think I have an extremely visceral explanation of this, but I think the best understanding I have is related to the previous question. And this is that ultimately, violating effects or anything with CP or flavor, you can usually construct your theory such that they occur in the off diagonals of some matrix, and all of the conserving parts usually appear down the diagonal. And because I ultimately think all of these bounds can be reduced to some matrix is positive semi-definite, then this is why these sorts of results have to come out. I mean, is that some really deep physical explanation? I don't think it is yet, but this is the level at which I understand it at the moment. I think really understanding why causality would imply this, for example, is not at all obvious to me. Like, because there's many steps, as you've probably appreciated from your own work on the topic as well, from these basic assumptions to where you end up. And understanding exactly which one of this is driving, I don't have a really deep intuition for. I think it's a very interesting question.
Oh, thank you very much. Yeah.
It's very similar.
I'm wondering if there will be some exception for this, if other concrete example. I'm not sure.
It's very similar to obtaining the vacuum stability bound, right? It's absolute vacuum stability bounds. The potential greater than 0.
Yeah.
Taking the sum of them and the octagonal components corresponding to the mixing between different fields, something like that.
Yeah, so I'm not as familiar. I mean, I understand what you're saying. I can certainly see that there's this connection here, but I'm not as familiar with this. Can you ultimately reframe those results as some matrix is positive semi-definite, or it's just like some intuitive that the off-diagonal parts can't be too large?
Yeah, there might be.
I'm not sure. Yeah,
there might be some better study.
Yeah, it may be very similar. I mean, intuitively, it sounds very similar, but I'm not sure. I'm not familiar whether anyone's formalized it into that exact language. But
Yeah, it's yeah, right.
Do you have any other question?
May I ask a question? I am very naive. I don't still organize my idea yet.
Please,
but,
no, go.
Yeah. So, for example, just looking this Lagrangian, we get the constraint from positivity, and also you have a similar fermion Lagrangian, and we get the independent constraint by taking the positivity consideration.
Yeah.
And but if we consider, for example, supersymmetric system,
yeah,
their coefficients should be correlated, right? Somehow. So I wonder, this kind of argument can exclude a kind of supersymmetry or something.
People have, no, it's an interesting question. I must admit, I haven't dug into this myself, but I believe in, so why maybe haven't people studied the SUSY case exhaustively? One of the reasons is that historically, it's only relatively recently people figured out how to do all of this for fermions. I mean, I didn't go through the details here, but as I'm sure everyone's aware, fermions throw minus signs all over the place. And in this whole game of determining whether something is positive, that's a nightmare. So it was quite, I mean, it was a bit technically challenging to put this in. The first work that I'm aware of that did this systematically is this Bellizzini paper, Brando Bellizzini from 2016. And from memory, actually, he goes through a SUSY example there and shows that, no, you can actually make this consistent. And to give you some more intuition for this, like SUSY as a UV completion is unitary, local, and causal. So it must obey these bounds in some sense. Like even if you break SUSY and then run below, it can't violate these bounds because it's a very sensible theory. Or it's a conventional theory in the way we normally think about it. So if SUSY violated these results, something would be going wrong with what I did, not with what with SUSY. It would be the claim. But I mean, that's a very vague statement. Let me point you to this Brando paper where from memory, he worked through a SUSY example and showed that everything goes through.
Yeah, I think I'll take a look at this paper, yeah, in detail, yeah.
That's a very interesting question. But yeah, for a long time, people hadn't worked out how to do this for fermions. So people had just not really tackled some SUSY theories, but I'm pretty sure from memory that the Brando paper does talk about a supersymmetric example. Or if it's not this, Brando's had a couple of papers on similar topics. It was one of his papers, but I think it was this one.
Okay, thanks.
Are there different effects of dimension 6 operators regarding the positivity? Because you just take the similar positivity bound, try to get positivity bound on dimension 6 from by taking different integral. But by taking the first derivative of the amplitude.
Yeah.
But maybe dimension 6 operator could contribute to the amplitude at the loop order.
Yep.
In such a way that it is contributing S² term. I don't know, model dependent, but suppose you have S² coming from the radiate corrections with the dimension 6 operators.
Exactly. Yeah.
Applying this previous argument on dimension 8 operator on that correction, something like that.
No, you're exactly right. And this was actually going back to the question by Carlo very early in the talk about the running. So the loops you're talking about will cause these coefficients to run. And this is exactly what was worked out for the case of the SMEFT by these authors in this paper here. And what you find is that the dimension, so Grant and I derived a bound like this C phi to the 4 has to be positive, okay? But really, physically, what we derive is that some amplitude has to have a coefficient that is positive, or the S² part of the amplitude. For weakly coupled theories, there's a one-to-one mapping between that and some single Wilson coefficient in the amplitude. In the Lagrangian. As I start making the theory more strongly coupled, where I can't neglect loops, for example, this breaks down. Now, the first breakdown is you need to include loops, as you said. But what these authors found is that you get, this is the running, for example, that's induced on this coefficient, and it comes in this form here. And what is interesting about this is that, you know, the way it all works out, when you move below the scale of new physics, this log is positive, and so this whole quantity is positive. But you can see if you start running the other way, you get a negative contribution. So it all works out beautifully the way that it must. But then to push this logic further, what if the UV was strongly coupled? Well, then the arguments become a bit more nuanced, and there's certainly no simple mapping between the amplitude and the Wilson coefficients, because it's like a many-to-many mapping, because, you know, there's very complicated results going on. There's a lot that's been understood, however, about what you can say about in strongly coupled theories, but that's very much beyond the sort of picture that I've been talking about in the talk here. Yeah. So you can do this much more generally, but at least in this very explicit calculation, they did exactly what you're talking about, and they found, okay, everything works as it must. Yeah.
Maybe, sorry, but let me ask another question.
Please.
Let me ask your opinion on, although you didn't include gravity in your presentation, there are a lot of papers talking about gravity.
Yep.
And the modification of the positivity bound because of that. Today, I think that there's some paper.
Most days there's a paper, honestly. It's a very active job. I missed the one today, but yeah, there was a paper by Brando, again, the same Brando, and Francesco Riva had a paper.
Francesco Riva, right, the massive gravity is not positive.
Yes, exactly. That's it. Yeah, I did see this paper, although I haven't read it yet. Just to say my rough intuition for what gravity does, gravity allows these coefficients to be slightly negative. And why does it do that? If you, let me not pretend I have the deepest answer to this, but there's a very simple way of seeing why gravity might allow things to be slightly negative. And that is because if you look at the causality version of these arguments, if your coefficient is slightly negative, it seems like it's slightly superluminal that you have going on here. But gravity actually, through the Shapiro time delay, will allow you to have things be slightly superluminal, but have no macroscopic acausality. Is essentially what can happen here. So roughly, gravity allows these coefficients to be slightly negative, but in the exact way that it does, and exactly how you include gravity into this is an extremely challenging question that people have thought about for a long time. There's been a huge amount of progress on this. In fact, I think at the very start, I had there was a Snowmass paper on this, which sort of summarized the state of the art, although that is probably now out of date, given how often papers come on this. And if you want to know much more about this topic, there's by Claudia Durham, who's done a lot of work on this, led one of these Snowmass papers. So that's a really good reference for this. It's a very interesting and open topic. Like, even what can this say for the SMEFT? Probably, the allowed amount of negativity is very small. So my impression is that this probably doesn't matter that much for the types of phenomenological studies that I'm thinking about here. But I'd be very happy to be shown to be wrong about that. That would be very interesting.
And then about the UV contributions, because normally we are assuming the UV contribution to zero. Even for dimension 8 operators. Dimension 6 operator is more strong assumption to set the boundary term to zero. But even for dimension 8 operators, do you think, is there any issue with the boundary, some remaining boundary term?
So this actually was considered in this paper, one of the ones I had in these blue boxes, by Moldesena and Sasha and collaborators back in 2016. And they showed that if the UV theory is causal, which gravity is, then that's enough at dimension 8 to kill the boundary term. So for dimension 8, it's okay, I think, but there are many subtleties once you add gravity in. Like, the graviton pole is something that people for a long time struggled how to understand. There was some work by Simon Caron-Fu and collaborators recently showing how you can deal with this. But yeah, it's something that people have worried about for a while. So that's a really active I mean, this on the formal side, this is a huge literature where people are constantly trying to understand this, and they're the most thing they grapple with is gravity. The sort of slightly lower brow approach that I've been taking here is taking some of the results we've got from these very interesting formal things, but then applying them to EFTs that we really care about as phenomenologists, because I think that that's a much less well-explored space.
Okay, thank you.
Yeah, maybe because we consider the partial UV completion as a not small mass gravity, but large table scale KK graviton theory in our work. So yeah, in this case, because of the partial UV completion, we assumed a bit the boundary. But if this partial UV theory or Kaltak-Klein graviton theory, table scale Landau sample theory, naturally connected to the UV theory of the which contains the axiomatic principle of the positivity, then it should be fine from the Crow-Wasser bound. Yeah.
Yeah, there's some. Yeah, of course, the UV unitarity also some. Yeah, there's some assumptions in the UV physics. Yes.
And I didn't see the detail of the today's paper yet. I think this today's paper is for more small mass graviton case, because we consider the very large mass table scale graviton theory in our work. But I think that we found that in our table scale graviton mass case, we found that this satisfies the positivity in our case. So I think theory is different from today's paper and ours. What do you think about it?
I haven't had a look yet, but I skimmed like a plot. I mean, their statement is that for certain values, this thing violates, but not all values. It wasn't like massive gravity is always in violation of positivity. Their statement was it can be in violation of positivity. But I haven't had a chance to digest it in more detail than that. So it's certainly possible that the two statements are consistent, like yours and what they're finding. But I mean, massive gravity, as you're aware, has been a very challenging topic for many years. There's many subtleties in there.
Yeah, right. Yeah. Oh, thank you very much.
Massive graviton is different from KK graviton.
True. Yeah. No, that's true. Exactly.
Yeah.
No, thank you.
Cosmological. I mean, it's a large scale. It's a massive gravity.
Thank you.
Very small UV cutoff.
Can I have one last question? Thank you for the nice talk. So as you just mentioned, the positivity from of the dimension 8 operator can be derived from the 4-bit the superluminal modes, right?
Yeah.
So in that sense, it's quite, to me, it seems quite natural that CP violation term should be smaller than CP conserved term. And then my question is that, is there any argument like that to dimension 6 operator? I mean, there should be some constraint.
No, good. So let me just say a few words about this, although this is a massive topic. The dispersive argument I like because it's very mechanical. I know there's many steps involved, but I know how to write down all the steps, and then it becomes it's trivial. Like if I go from dimension 8 to dimension 6, I know what I have to do mechanically. Sure, I can't write down something's positive, but at least I know what to write down. It is very unclear these causal arguments are much more subtle. Like to give you an example, if you add gravity into the causal case, it becomes a very challenging thing because constructing, there are known examples like in QED, one of the polarizations to a photon can travel far, can be superluminal in a Schwarzschild background. This is something that was known from the 80s, but you can still check that you can't create any closed time-like curve in that theory, which is what you're most worried about. Like these things become much more subtle in gravity. And in fact, more generally, sorry, go ahead.
No, we are just ignoring the gravity, right? In this case, so
I wouldn't go there. I'll say this, I'm ignorant of gravity. I think many people actually know a lot more about this. So there's been a huge amount of work. So don't let me give you the impression we don't know a lot. I'm just not an expert on that. But there are, again, subtleties. But more broadly, people have studied what do you get from the dispersive results and the causal results. And in many cases, in all the cases I showed you here at dimension 8, you get the same. But in other cases, they can diverge. You can get stronger bounds from one than the other. And even why you would get the same bounds, I think is, to me, still a mystery. And I've talked to some other people who are experts on this, and they honestly, I don't think we have a really good idea of why these two results are giving some similar physics. Because to say, like, this causal argument feels very classical. You really just do it. It's something that goes wrong in the infrared. You just do a simple scattering. You can simply show that in the infrared EFT, I can construct a closed time-like curve. Whereas on the dispersive case, it involves unitarity, which is not obviously being invoked on the other side. It involves analyticity, which is not obviously being invoked on the other side. So the fact that these two match up, I still think is very mysterious. And no one's even extended the causal arguments to fermions, for example. I'm sure it probably can be done, but exactly how that would work through, I think, is just, it's not super clear. So people haven't sat down and figured it out. So the dispersive case, it's very mechanical. People know what to do. The causal one is very interesting, but exactly how to extend that in each case has not been worked out. And I have no idea how you would do this at dimension 6, for example.
Okay, I see. Thank you. Thank you very much.
Yeah, no worries. Yeah, if you sit down and do the calculations, you'll find that the various things are out of phase, whereas at dimension 8, they're in phase, so you know how to put this down. It's just the cause. I've tried a bit to try and get the causal to do something at dimension 6 from the causal, and it wasn't obvious to me how to make this work.
Sorry, question again.
Please, yeah.
If there are no method about how to deal positivity with path integral method?
With path integral methods? I mean, ultimately, I guess it depends exactly what you have in mind here. It's not, I mean, of course, I can compute the sort of quantities that I'm trying to constrain here in either formalism, and I should get the same result. And I will just get the same amplitude here. So it's not immediately obvious to me what you would gain by looking at this from the path integral formalism, but I'm probably missing what you have in mind there.
Sorry, I actually thinking about some case of the very strong interaction between particles. I mean,
yeah.
So in that case, you usually think not a perturbative method, but path integral way to calculate. So if I know.
Possibly, yeah. No, there's been some work on, I mean, Riccardo Rattazzi had a bunch of papers after this where they just made some statements about strong coupling cases. I actually don't remember the details off the top of my head, but maybe they have some statements to that effect. So that might be a good place to look. But yeah, no, it's an interesting, I just can't say more at this moment.
Thank you.
May I ask one just a small question?
Yes.
Of course, just to say, I will have to run in 5 minutes, but I'm very happy to answer some questions.
What time is it in CERN now? What time?
It is 10:25 in the morning.
10:25. I'm just curious, do you have in your mind for the UV theory of positivity violation? Yeah, some theories of the Lorentz violation or something, for example, but do you have any good UV theory for causing positive vibration? I'm not sure.
Well, as of this morning, massive gravity, possibly. But beyond that, I think the famous example was the one that was really the motivation and what was studied in this original Alan Adams paper. There's this theory of DGP gravity, where gravity, gravity becomes, I'm probably going to get this completely wrong, but gravity starts to behave like 5D at large scale. So you get modified versions of the way that gravitational interactions work. Was it, anyway, I'm probably mucking that up. I forget the exact way it goes, but it was some modification to gravity. And for a long time, it's a very exciting theory in like the early 2000s, and people were trying to understand how you could UV complete this into string theory. and no one could. And then the reason is because it violates these positivity bounds, and string theory satisfies these. So you could never embed this into that. So that was what was shown in this, is that this DGP gravity violates these bounds. And so that's the example that I'm aware of. But just to say, like, I mean, you'll never be able to use these bounds to rule out some simple theory of dark matter or something like this, because all of the theories we usually write down satisfy unitary causality and locality. So they should be fine. It's more just the, it's usually you have to do something that is counterintuitive, like these odd theories of gravity is the examples I'm aware of.
Oh, thank you very much for a clear explanation.
No, good question. Thanks.
If we have still 2 minutes, I have one last question.
Please.
Okay, so it's quite naive, but still, in your first example with the, let me say, the Euler-Heisenberg plus something Lagrangian, I guess we can use as an argument for the fact that you're going with the dimension 8 operators, and you're really making the connection with CP violation, the fact that, well, these are the first operator that I expect to see because of gauge invariance. Okay, so I take the principle of gauge invariance, I expect these are the first operators. So I would expect that these are the dominant ones. But if I look at the fermion case, I would expect a dimension 6 operator in the form of a Grosvenor-like term, right? A psi bar psi square. And this one, I cannot access it with all these, let me call them games with this derivative of S, this kind of stuff, because it's a point-like interaction in the form of the Grosvenor.
No, of course.
Saying.
Yeah.
And
exactly.
This one, I expect it to be the dominant one, because it's a dimension 6 operator. So if in the first case, I see the connection because I expect the CP violation to come from dominantly from those terms. Here, there's a term that is hidden to your method, but that might be the one that determines possible flavor violations. So,
absolutely,
how can you make the link?
I in general, I can't. I think you're hitting on the exact right point. It's a slightly UV dependent statement, and this is why I want to learn what we can say at dimension 6, even if it's harder, because for a generic UV theory, exactly as you're saying, you'll get the dimension 6, not the dimension 8. Now, in principle, you can distinguish the different operators. Like if you do enough angular measurements, for example, the different parts tease out. But to say there are UV completions where I can generate dimension 8 without dimension 6, like if you stare at this, if I wanted to UV complete this at tree level, I have to put something in between that has spin 2, because I need to couple to this spin 2 current. And so if you have some, there are like KK graviton theories, potentially it was similar to what Kimiko was describing, but where you will generate these dimension 8 operators without lower dimension 6. But it's very specific theories. The generic expectation is you get dimension 6, and that's exactly why I'm trying to understand this. But the nature of it is the sharpest statements I can make are at dimension 8. Yeah, so you're exactly right. If I just see flavor violation without many more studies, I would assume it's coming from some dimension 6 operator, and the cleanest version of what I'm saying here wouldn't apply.
Yeah, I think the KK graviton can induce flavor violation at the loop order. So probably you can interpret your flavor violating operators in that way. At the level of dimension 8 operators, of course,
Interesting. Yeah, I didn't
this is
know
violation. I mean, flavor violation to the standard model, CK. Without extra flavor violation in the beginning, but probably you can induce it by the known sources.
Unfortunately, I will have to run. There's another meeting that I promised I would attend, but I'm very thankful for all of the questions. And if there's more questions, also feel free to send me an email. I'd be happy to chat more.
Thank you very much. We need to invite you again.
Thank you. No, I'd be delighted. This was really a pleasure.
Thank you all for your time seminars, lectures,
for your questions.
Thank you.
Thank you very much.
Thank you. Please send your top slides so that I can share them with other
people. Will do. I'll send them straight away.
Okay. So
thanks everyone.
Thank you. See you next time.
Thank you. Bye.